I guess we. Okay, so it's a pleasure to have Antonella Palmese talking to us today. Antonella did her undergrads and masters at La Sapienza in Rome, and then continued doing a PhD with Ofer Lahav and Philippe Abdallah at University College London. She then went for a postdoc to Fermilab in Chicago, continued working on DESI, and is now NASA Einstein Fellow at UC Berkeley. And we're all, so yeah, you can go ahead and talk about something. I guess people want to hear you talk, not me.
Okay, great. All right. Okay, so well, thank you everyone for coming today, especially after the holiday there. So today I'll be telling you about probing the universe expansion and the origin of compact object binaries with multi-messenger astronomy. And by multi-messenger, I mean with the use of both gravitational wave data and optical data, mostly from the dark energy camera and the dark energy spectroscopic instrument. So here's an outline of this talk. So first, I'm sure that this is a repetition for a lot of you, but I'm not sure who is aware of the different surveys. So I will give a brief introduction about dark energy survey and the dark energy spectroscopic instrument. And then I'll move on to telling you about the gravitational wave sources that are of interest for this talk and how we can use those to understand the Hubble tension as gravitational wave standard sirens. So I'll tell you about where we stand in terms of current measurements and prospects for the futures with standard sirens. And then I'll talk for a few slides with about peculiar velocities with gravitational waves, and that's something that we are thinking about for the future. And then at last, I'll tell you about some potentially interesting information channels for the origin of gravitational wave binary black holes. So let me start with the dark energy survey. So this was in the end, it was a 6-year survey that took images for about 300 million galaxies over 5,000 square degrees over this tank-shaped footprint that you see here. So this is the wide field DES program. So this was taking data in G, R, I, Z, and Y band, and this is what we use to derive the photosys that will be used later on in my talk. We also had some time domain programs, a supernova program taking images of about 30 square degrees of the sky repeatedly every week. And we also had some follow-up, multi-messenger follow-up programs, in particular the high energy neutrinos from IceCube follow-up, and then the follow-up of gravitational wave bands from LIGO and Virgo. And I'll just point that because the dark energy camera, so the instrument that was built for the dark energy survey, is a great instrument, even still now, to do follow-up of gravitational waves, we are still using it to keep following up this event. So beyond the end of the dark energy survey that ended in 2019. So obviously the survey finished taking data, but we're still analyzing the DES data and producing cosmological analysis. So the dark energy camera is a great instrument for probably one of the best instruments still for gravitational wave follow-up in the optical, at least in the southern hemisphere. One of the reasons being that it has a decently large field of view, about 3 square degrees, and it also mounted on a 4-meter telescope, the Blanco telescope at CTIO, which lets us go quite deep in decent amount of times, which is what we need when we're trying to find this very faint, at least compared to a typical supernova, this very faint kilonova that we expect to be associated with binary neutral star mergers. And I'll just point you here that there's a wealth of public data from dark energy survey already, including the year 6, so the final photometric deep catalogs over this entire footprint. And also the year 3 gold catalog has recently been released, including all of the value added that you might be interested in, like photometric redshifts. Okay, so let me switch to DESI. I'm sure that many people here are aware of what DESI is. But just a few words, this is obviously different from DES because it's a spectroscopic instrument. It has 5,000 fiber and it's mounted on the 4-meter telescope, the Maya 4-meter telescope at Kitt Peak. It also has quite large field of view, about 8 square degrees, which is very nice when we're trying to follow up this gravitational wave localization that tends to be usually at least a few tens of square degrees. But it's also interesting that DESI will take data for more than 30 million galaxies over 14,000 square degrees, which means that we will also have a lot of potential host galaxies for gravitational wave events. But what matters for the specific talk is the legacy survey. I'm sure people here know about it, but just a few words is that the DESI imaging survey was taken before the start of the DESI experiment so that the targets could be defined to be pointed by the fibers. So where do we stand in terms of DESI spectroscopic observations? Well, we started taking data in 2020 and we're currently finishing, we're near the end of year 1 data taking. And so I always like to point out that this was already in January when we were something like 12% through the total time of the main survey, and we had already taken more galaxy spectra than all of the previous spectroscopic experiments combined. So it's a very exciting time to be part of this experiment. Okay, so what are the gravitational wave sources that I'll be talking about in this talk? So here we're talking about detections that can be made from ground-based gravitational wave detectors. So in particular, second generation gravitational wave detectors. So we're talking about the LIGO detectors, the Virgo and the Kagra detector. And then I'll also mention about for the pure velocity part, about next generation, so third generation gravitational wave detectors, still ground-based, that are expected to come online at some point in the 2030s. Hopefully the Einstein telescope in Europe, and also the Cosmic Explorer in the US. So these are the experiments that I'll be taking into account, and they're mostly sensitive to the sources that I'm showing you here. So binary neutron star mergers, binary black hole mergers, and neutron star black hole mergers. And you'll see these acronyms throughout my talk: BNS, VBH, and neutron star and NNSBH. And here you see a nice picture that will come back later from the LIGO, Virgo, and Kagra collaboration, showing you all of the detections that have been made so far by those detectors. So in particular on the y-axis, you see the masses of the objects that merged. You see the 2 objects in the binary given by these first 2 points, and then the third point is showing you the mass of the remnant object. And the different colors, in particular in blue, you see the black holes, and in orange you see the neutron stars. So we're already at something like 90 detections. Okay, so now what is the motivation to use this type of sources to measure something like the expansion of the universe? Well, the Hubble constant tension, I'm sure all of you are aware. So the Hubble constant tension is basically a 4 to 6 sigma discrepancy between early time measurements, in particular from the cosmic microwave background from the Planck experiment, and the late time universe measurements from supernovae type 1a, in particular, anchored to Cepheids measurements. So the question that we always like to ask is whether this discrepancy is coming from systematics that we have not taken into account in either one of both of these probes, or if there is some new physics that needs to be taken into account, in particular, for example, when measuring the Hubble constant from the CMB, this measurement that is in the significant tension is really the one that is coming when one assumes a flat lambda CDM scenario. And if there is something that goes beyond this flat lambda CDM scenario, then this measurement could be biased. So one way of trying to understand better this tension is to get an independent measurement of the Hubble constant, independent from both of these probes. And in particular, if this is coming from the late time universe, like the gravitational wave detections that I showed you in the previous slide, then these should be ideally independent of the distance ladder that supernova type 1a measurement that is in this significant tension is using, so that we are hopefully completely sensitive to a completely different set of systematics. So standard sirens do offer this possibility. Standard sirens work very similarly to standard candles. So you can get a distance measurement. In this case, you get it directly from the gravitational wave detection. So you don't need any distance ladder to retrieve that. And then if you're able to identify a counterpart to that gravitational wave event, and ideally an optical counterpart like the one that we found for 170817, then you can identify the host galaxy and get a redshift of that and populate this Hubble diagram and fit the distance redshift relation that, at least for the lowest redshifts that we'll mostly be focusing on here, is sensitive to the Hubble constant. So there's several ways of making standard siren measurements. The ones I'll be focusing on here are those that take into account, that make use of galaxy redshifts. But you can make other assumptions, for example, about the, and I'll mention this a bit later. For example, you can make some assumption about the mass distribution of binary black holes or binary neutral stars to break basically the degeneracy between the mass and the redshift in the redshifted mass that the gravitational waves measurements can make. And so that way, by making this assumption, you get a redshift directly also from the gravitational wave detection. And so you can also make a standard siren measurement. Obviously, the cleanest way is to do this with the counterpart, because you get a very clean measurement of the host galaxy redshift. And so this is most powerful, at least in my idea, standard siren method, the one where we have a counterpart, a unique host galaxy identified. In this case, we talk about the bright standard siren case. And we hope this to be the case for almost all of the binary neutral star detections that will be made from LIGO, Virgo, and Kagra, and for hopefully also a fraction of neutral star black holes that could be also very powerful standard sirens. In the case in which we don't have an electromagnetic counterpart, then we talk about the dark standard siren method or the statistical method. And what we do is we take into account all of the potential host galaxies within localization volume within a statistical framework, hence the name, to measure, to get this redshift distribution that we use then to measure the Hubble constant. So let me start with a few words about the first method that I'm sure everyone has heard about, the detection that was made for GW 170817. This was the first gravitational wave to come from a binary neutral star merger, and also was the first one, and so far really the last one, to have an associated electromagnetic counterpart. And here you see this nice picture from our DCAM discovery paper, where you can see the kilonova detection here in the DCAM images. So it was exactly the fact that we were able to pinpoint exactly the location of the optical counterpart that we were able to identify the host galaxy. And so this is the first measurement of a standard siren, basically in this paper that was led by the LIGO and Virgo collaboration, and showing you here the posterior on the Hubble constant with the 1 sigma uncertainty shown here. Obviously, if you compare this with the two measurements that we saw earlier in the plot of the Hubble tension motivation, in particular the CMB1 here in the vertical bands in green, and the supernova measurement, although this is an older one, in orange. Obviously you see that the 1 and 2 sigma uncertainty given by these vertical lines are much larger for this one gravitational wave event, but this is expected because obviously it's just one event. But in the future, this will be a great way to try and understand the Hubble constant tension. First of all, because I mentioned that this method is self-calibrating, so it's independent of the distance ladder that is used in supernova cosmology. And it's also cosmological model independent in this case, because it's these events are so nearby, they're really only sensitive to the Hubble constant. And then a couple of limitations to mention is the fact that one has to obviously take into account the peculiar velocity of those host galaxies, especially because they are so nearby. So that becomes also a limitation. And also the inclination angle is highly correlated with the luminosity distance from the gravitational wave measurement. And so this basically contributes to most of the uncertainty, well, a lot of the uncertainty together with the pure velocity that you see here for H naught. This is because this degeneracy between the inclination angle and the distance becomes a degeneracy between the inclination angle and H naught, as you see in this plot. One can try to break the degeneracy by constraining the viewing angle from the electromagnetic observations, and that can improve the precision by a factor of a few. And that becomes very important, as we'll see later as we combine more and more of these events. Okay, so let's move on to the other method, which is the dark standard siren method. The reason why we are interested in making a measurement of this kind is that there's many more binary black hole detection than there are binary neutron star detections. So by default, we'll have many more events without counterparts than events with counterparts. And on top of that, we also know that we are going to miss some of those counterparts because they're just really hard to find. So we have all of these events that are sitting on top of our galaxy catalogs. And so it makes sense to try and make a measurement of this kind. So here I'm showing you a slide on simulations just to show you how the method works. So this is a DES-like galaxy simulation on top of which I simulated gravitational wave events. And basically assuming an H naught in this case of 70 kilometers per second per megaparsec. And then you can try and recover the Hubble constant from each one of those gravitational wave events. And so the single event posteriors is what you see here in these plots. These are the gray lines are single event posteriors. A couple of those are highlighted in color so that you see better how they look like. And you'll see that each of those will have some peaks at different values of H naught. And this is totally expected because these peaks correspond to the large scale structure along the line of sight within that area that you see here. Basically, we're getting the redshift distribution of all of the galaxies, and each of those overdensities that you have along the line of sight will correspond to a specific value of H naught given the distance of the gravitational wave event. So if you only had one galaxy, you'd expect, or one overdensity, you'll expect one peak. If you have multiple overdensities, you'll expect multiple peaks at different H naught values corresponding to their redshift. So then what happens once you increase your uncertainty on the luminosity distance or the redshift is what you see when you go from the top panel to the middle panel. And so this is increased uncertainty on the distance. And then if you increase the uncertainty on the redshift, you get what you see when you go from the middle to the bottom panel. So basically these peaks just become broader, which is something that you might have expected. The important thing is that after we combine enough of these events, we're really thinking about hundreds of these events, in this case, well-localized events, you would be able to converge to the input value of H naught. And the combined posterior from all of these events, in this case, these are 100, is shown by these black lines in each panel. So you see how we recover the input value. Okay, so where do we stand in terms of current measurements? So I already told you that we only had one counterpart so far. So basically in the last observing run by Lago and Virgo, 03, that was between 2019 and 2020, we did follow up also with the dark energy camera within the DESI GW program, several of those events. There were more than 50 alerts, and between our observations and other groups' observations, there was no convincing counterpart to be found. So you can see a couple of the DS papers from our group here. So in terms of standard sirens analysis, all we're left with was to localize, to look at the well-localized events and make a dark standard siren measurement. So in particular, we started from GW 170814. So this is from, as you can see from the name, right? The name reflects the date of the detection. So this was an event from the previous observing run, 02, and we use this event because it falls right in the middle of the ES footprint, as you see here. We used it to make the first measurement of the Hubble constant using a binary black hole. And then we extended to this other event that is still the best localized dark standard siren from 03 GW19 0814. It's also very interesting astrophysically object because it contained either the lightest black hole or the heaviest neutron star ever discovered in a binary. And it's still unclear whether this was a neutron star black hole or a binary black hole merger. But for standard siren, what matters is that this is a really well localized event. Okay, so going beyond the dark energy survey, we have the DESI imaging, right, that covers a lot of the sky. So we can also extend to other well-localized events from the last observing run that are covered by the DESI imaging. So here you see a selection of the 8 best localized events. So we picked the top 20% based on the co-moving volume. And we picked those that were covered by the DESI imaging out of this top 20%. So we're really making a measurement that is using well-localized events and also high completeness galaxy catalogs. And that allows us to basically have a better handle on the fact that these measurements can be also really, if you don't have a complete galaxy catalog, can be really dependent on the assumptions that you make on the mass distribution of the black holes. So some of the systematics analysis that were included in our work were mostly related to photometric redshifts. So basically some of the things that we looked at were correcting a bias that we expect when we look at the bias that is measured from a validation sample where we have spectroscopic observations. And so we correct for that in our final posterior. We take into account also full redshift probability distribution function for each of the galaxies, in particular in the DES analysis, and see how that is actually better than just using a single measurement with a Gaussian error for each of the galaxies. We also take into account gravitational wave selection effects that are particularly important to take into account, otherwise you get a biased measurement of H0. So the way we do that is basically we try to define a selection function of gravitational wave events for different cosmologies and derive that as a function of redshift and take that into account in our posterior. And this is what you see here in this plot, the selection function of the gravitational wave events. We do that with simulations, with simulated gravitational wave events. Okay, so other systematics that, again, need to be taken into account are what I mentioned earlier, assumptions about the black hole mass function, particularly if you see the work by the LIGO, Virgo, and Kagra collaboration, they show how this is very important in this type of measurement. And I think some of the systematics that still need to be explored are, for example, what are the different expectations in terms of what type of host galaxies we expect to host this binary black hole mergers, assuming different binary black hole formation scenarios. Now we're starting to understand that there potentially is, we'll see later, multiple different formation scenarios for these black holes that will tend to happen in different types of galaxies. So what happens to our H0 measurement based on each formation channel? It's obviously something very complicated to analyze, but we should start thinking about it. And also how we can marginalize over all of the assumptions that one can make on the black hole mass function. Okay, so here I'm showing you the latest constraint that I made using dark standard siren and combination with GW170817. So the measurement from the events that I showed you earlier that are covered by DES and the DESI imaging from the dark standard siren alone is shown here in the blue curve, by the blue curve. And then if you combine that with GW170817, shown here in this gray curve, you get this final combined black posterior with the 1 sigma uncertainty shown in this slide. So one of the main conclusions is that the dark standard sirens provide about a 30% improvement to the precision of GW170817 alone. So it starts to be a significant contribution to the standard siren measurement. And I will also point out the fact that in this paper that I mentioned also in the previous slide, they also provide another measurement using a different galaxy catalog and a slightly different method. But in particular, they also provide a measurement that only uses the gravitational waves. As I mentioned earlier, you might also try to make some assumptions about the mass function basically of these black holes and get a redshift estimate that way. So they also provide the first of this kind of measurements using all of the gravitational wave detections that have been made so far. And even though these measurements are not very constraining at this point, I think eventually it would be interesting to start combining both of the methods, well, all of the three methods, right? Also because the dark standard siren method without the counterparts are really complementary to each other. So in the case in which you're making assumptions, for example, about the mass function of the black holes, you're really sensitive to the most distant and less loud events. While in this case, I'm focusing on the well-localized, loudest events that are also more nearby. And so eventually it'll be interesting to combine all of those methods together. I will also mention that all of these measurements that I showed and that you can find in these other papers are consistent both with the early and the late time universe measurements of H0 that we've seen before. And so they don't provide any insight at this point in the Hubble constant tension. But in the future, they will become interesting to provide some insight in that. So here I'm showing you some simulations for future constraints. So here again, I'm showing you binary black hole gravitational wave simulations on top of a DES-like galaxy simulation. So here, though the detection of the binary black holes are simulated what we expect from LIGO, Virgo, and Kagra at design sensitivity. And so here is, again, in color, you see the single event posteriors, and then you see the combined posterior here in black. And what it tells you is that if you have something like 200 nearby detections, like the one that we selected before in the DS plus DESI analysis, then we can get down to about 2% statistical precision on H0. And so this is what the type of precision that we'll need, right, to try and weigh into the Hubble constant tension. So this is what we expect from this DES galaxy catalog, and something similar is expected also for an analysis that will come out from of dark sirens with LSST, for example. Obviously, we can think about doing something similar also with DESI, which will be probably much more interesting, so that we don't have to worry about all of those systematics with photosys that I mentioned earlier. And so, in particular, from the dark standard siren case, again, the forecasts show that we should be able to reach about 2% uncertainty on H0 with a 5-year long run of LVK of the LIGO, Virgo, and Kagra detectors at design sensitivity. The cross correlations will also be interesting, not only to measure cosmological parameters, but also to measure, for example, the bias of binary black holes and tell us something about the origin of these objects. In terms of bright standard sirens, the way DESI could try and contribute is by producing a quick classification of all of the counterparts that are found by imaging at the location of this gravitational wave events. So here is a follow-up run that we did last year for this well-localized event, 190412. The 90% credible interval area is shown here in green. And then you see the pointings that we took with DESI here in red. So this is showing you that basically with just 2 pointings, we were able to cover a lot of this high probability region for this gravitational wave event. We did this as after LIGO, Virgo, and Kagra were actually offline. Unfortunately, we didn't get much overlap, or at least DESI was not ready to produce any follow-up before the third observing run was off. So we did this as a test for future targeted opportunities that we might do already next year. And so we still tried to do it as a live search. So we looked for live transients in the area, at the same time trying to target, because the live transients are something like in the order of dozens to hundreds. And then you can also use the remaining fibers to target potential host galaxies, also to understand whether they are at a redshift that is compatible with the gravitational wave event in case you find some transient, but also for a dark standard siren analysis, again, it's interesting to target these host galaxies. Okay, so assuming that in the future we'll be able to identify this kilonovae, in particular in this case, since we're talking about the quick optical follow-up, assuming that we are able to find these counterparts, how many events do we need to reach that 2% uncertainty on H naught that I mentioned earlier? So here you see the expected uncertainty on H naught as a function of number of events. And if you focus on the orange line, you see that you need something like 50 events to reach that 2%. But if one is able to also include some information for the inclination angle, so at the level of what was done from the kilonova alone for 170817, then you're able to bring down this uncertainty to the blue curve. And so potentially you can reach that 2% uncertainty on H naught with a dozen of events or so. So it's really interesting to find these counterparts, find them earlier so that we can better characterize, for example, the kilonova light curve and make measurements of its geometry. So the other thing I want to mention here about DESI and multi-messenger follow-up, although it's not really about gravitational waves, but it's still related to the same target of opportunity strategy that we're thinking for gravitational wave events. So we did also a follow-up of a high energy ice cube neutrino event a couple of months back, or more than a couple of months back now. It was September 2021. And this was done in a more non-disruptive mode, where the idea in this mode is that we just go and take and see if there is some DESI tiles that need to be observed at the location of our whatever event we're interested in. In this case, it was a high energy neutrino event. It could have been a gravitational wave event or a fast radio burst, and see, and go and observe that tile at that location so that you get the redshift of the potential host galaxies. And also you could hope to see some transients, as I was mentioning earlier. We're also trying to identify transients in the spectra alone, even without the need of any other external imaging information. And so here you see the location of one of this one ice cube neutrino event that we followed up, and one of the tiles from DESI that fell at the location that overlapped with the location of the event. We did not find any interesting potential counterparts. In particular, we were looking for collapse supernova and tidal disruption events, and we did not find any. And we reported this to the community. Okay, so now I'll switch to peculiar velocities and how we can measure this with gravitational waves. So I guess I don't have to tell to this audience that okay, peculiar velocities were mentioned in my slide on standard sirens as a sort of a limitation to the measurement of H naught, but they also do contain some interesting cosmological information that we can try to measure. So for those who are not that familiar with peculiar velocities, we're talking about the motions of galaxies on top of the cosmological expansion. These motions do follow the clustering of large-scale structure and also the laws of gravity. So if we can measure the peculiar velocity field, we can also probe large-scale structure and the laws of gravity. So one way of doing this that people here are very familiar with is to use galaxies that do have a distance measurement, like fundamental plane galaxies, or more recently also supernovae type 1a. And here we're suggesting that we can also use gravitational wave host galaxies that provide also a distance measurement to measure the peculiar velocity field, at least in the future. So because we'll need some very precise measurements of the distance, this is something that we think is only interesting for next generation gravitational wave detectors. So we're looking into this ICE telescope and cosmic explorer type of detectors. And so we make a forecast for the next decade. What we use is a peculiar velocity power spectrum, the overdensity power spectrum, and the cross correlation, and all of them depend on basically on this product between FD. And those in turn depend also on this parameter gamma, the growth index that depends on the gravity model. Okay, so let me show you some of our forecasts for the future on F sigma 8. So in particular, F sigma 8 in 3 beams of redshift out to redshift 0.3. So the expected constraints from first fixing gamma, the gamma value to the general relativity one. The expected constraints that we get are shown here by this blue triangles, and this is coming from the peculiar velocity fields as measured with the gravitational wave sources plus a redshift space distortion, basically from a combination of type and DESI, so that we're covering almost a lot of the sky. So as you can see, these constraints are competitive also with what we expect to get from a 10-year supernova survey, something that might look like LSST. And those are shown here by this orange triangle. And this is great because supernovae are also really good at measuring peculiar velocities. So it's good that we are competitive with supernova measurements as well. So in terms of numbers, we're talking about 3% precision on F sigma 8, again, with this 3G, third generation gravitational wave detector plus galaxy surveys. And obviously this is thinking about a 10-year kind of Einstein telescope experiment, but this could be less if we have more detectors like several Einstein telescope and several cosmic explorer detectors. So as you can see from this plot, obviously these different purple lines are showing you F sigma 8 for different values of gamma. And so if you're able to measure this well, F sigma 8 at this lowest redshifts, you're also able to discern between different values of gamma. So we then let the gamma index vary, and we find that you can get to a precision of about 0.02 to 0.03 on gamma, and that lets us discern between these popular gravity models that predict a value of gamma that is shown here, in particular DGB gravity models and FOR models. So in the future, this will become something interesting to do. But let's go back to the detections that have been made so far and think about the origin of some of those binary black holes that we used, for example, to make measurements of H0. So this is a picture that I showed you earlier from LIGO, Virgo, and Kagra. With again all of the detections, and now I would like you just to focus on the binary black hole mergers that are shown here in blue. So you'll see that at least a few of those have the component masses that fall within this region, the so-called upper mass gap, where because of positional pair instability and pair instability supernova, we don't expect the formation of black holes in these regions, at least from stellar evolution, while black holes of higher mass can be formed through direct collapse. So this is the first reason, like the detection of this black holes in this mass gap is the first reason why one might want to explore different possibilities for the formation of these black holes beyond standard stellar evolution scenario, and also population analysis of this gravitational wave events show that a mixture of different formation channels is actually preferred. So we don't believe that stellar evolution is forming all of these black holes. There's probably multiple ones here at play. And so these are the two motivations for me to look beyond stellar evolution scenarios. So I'll be telling you about two formation channels that are interesting, and they're related to central black holes in galaxies. And so the first one is the idea that at least the most massive stellar black holes that are being detected from LIGO and Virgo could be the central black holes, so very low mass dwarf galaxies. And we're talking about dwarf galaxies with a stellar mass in the range of 10 to the 5 to 10 to the 6 solar masses or so. So this type of dwarf galaxies have been observed in the local universe. So they do exist, and they possibly dominate the number density of galaxies in the universe. So the idea is that if you have, if at least some of these dwarf galaxies also contain a central black hole, like many of the higher mass galaxies do, then in the case these dwarf galaxies merge, then it's also possible that something like dynamical friction could drag the central black holes close to the center of the remnant galaxy, and that these two black holes might undergo the gravitational waving spiral that we can detect with LIGO, Virgo, and Kagra. So what's interesting about this formation channel is that it could, not only because we're interested in understanding the origin of these detections, but also it could give us some insight into the formation of supermassive black holes. So the idea is that we do observe these massive black holes at the center of galaxies, and they might have grown from smaller mass central black holes like the one that we're suggesting here through mergers and accretion. And so looking at this baby, basically central black holes, we could see perhaps what the seeds of supermassive black holes could be. So how does one test this this scenario? Well, in the absence of electromagnetic counterparts, for example, that can pinpoint a host galaxy and tell you whether that's a dwarf galaxy. Obviously, it's very complicated. There might be some emission coming from these black holes, but if there is, perhaps if they're slightly active, they have some accretion disk, that could be possible, but it's also possible that would be very faint to see. Even the host galaxy would be very faint to see, even at something like 700 megaparsecs, because we're talking about very low mass dwarf galaxies. So what we do is to first trying to start from what we know about this of the central black holes and what we know about dwarf galaxies. So we start from this known relation, the scaling relation between the mass of the central black holes as a function of the stellar mass of the host galaxy, and then we extrapolate that down to the lower masses of interest. So we're going down, for example, here to the specific event GW190521, which was very interesting because both of the masses in the binary fell in that mass gap. So very interesting candidate for this type of scenario. So then from the values of those masses and the scaling relation, we derive what we expect the stellar mass of the host galaxy to be. And again, we are in the order of 10 to the 5.5 to 10 to the 6 solar masses. So given this, this mass range, we ask, is the merger rate of dwarf galaxies in this mass range ever high enough to explain the observed merger rate of the binary black hole? So in this case, GW190521 like binary black hole mergers. And so this measurement from 190521 is given by the region between these two red horizontal line. That's the rate, the volumetric rate. And then we compare that with our expectations from dwarf galaxy mergers, which is given as a function of redshift here by the solid line. So the answer to this question is yes, we can actually match this, this merger rate if we go beyond redshift 1 or so. And that implies, in particular, for something like 190521, that was a redshift, I think 0.8 or so, implies a likely time delay between the merger of the galaxies and the merger of the central black holes that is in the order of 4 to 5 giga-years. So then we went and looked at the what would be the dynamical friction timescales for two black holes of those mass to be dragged to the center of the remnant host galaxy. And we find that it's actually in that time scale. So dynamical friction could actually explain this time delay. Now for the future, so what we find is that this formation scenario is actually plausible. And in the future, for example, we'll need something like simulations that go beyond the dynamical friction timescale and follow the black holes through the phases of stellar hardening and so on to see if they actually can merge. And this is very complicated because you need very high resolution simulations. but it's hopefully going to be achieved in the near future. We will also be looking at more binary black hole detections and looking at a population on a population level rather than on an event basis, looking at the properties and the rate evolution, whether the rate, for example, how it evolves with redshift and whether that's consistent with what we expect from dwarf galaxy mergers. So in the future, we hope to expand on this scenario to confirm it or rule it out, which is also interesting to say. We don't think that any of these black holes are actually central black holes of dwarf galaxies. So perhaps that means that these dwarf galaxies either have a black hole that is more massive and it's outside of the LIGO band, or these black holes don't merge for some reason. Okay, so now the last part of my talk is about this second very interesting formation channel for this, at least especially the more massive stellar black holes that are being detected. And in this case, we're still talking about something that is related to a central black hole, but in this case, we have a supermassive central black hole. And the stellar black holes that are actually merging in the LIGO band are orbiting around this, this supermassive black hole. The idea is that also this binary would be embedded in an AGN disk. So this supermassive black hole is actually active. And what is interesting about that, not only that you can have like migration traps and like you can have an assisted in spiral of this black holes thanks to the torques of the disk, but also the presence of the gas around the binary could give rise to an electromagnetic counterpart. And so for someone like myself, doing follow-up of gravitational events, this is very interesting. And it's also very interesting if we think about this potential candidate that was detected a couple of years back. So this was found in coincidence with an AGN flare. And this was close in time also with the detection of this event, GW190521. So this is a plot from the detection paper from the Zwicky Transient Facility, showing you the light curve in GNR band. So a GNR magnitude as a function of time. And you see how there was a peak after the detection of this event, GW190521. So this was very interesting. However, what we find is that there was a quite high probability of chance coincidence for this specific gravitational wave event. The reason for that is that this was also one of the most distant event, which means that its localization contained a very large volume. I think it was close to being to the very bottom of the gravitational events that we have so far, if you rank them by localization volume. So that implies that there are, especially as you go to larger redshift, a large number of AGNs, and in particular unobscured AGNs that can flare. And so we might expect to see a flare of an AGN in that volume, even if it's not probably associated. So even though we find that there was a 70% probability of chance coincidence for this one event, and for a flare of that kind, it's still interesting to ask the question, how many of these flares do we need to observe before we're able to say that there is actually a significantly an informative association between the gravitational wave events and the AGN flares. So we built this Bayesian formalism that is basically trying to constrain this parameter lambda, which is the fraction of binary black holes that induce an AGN flare. And we're looking for one signal AGN on top of some background AGN that are in the same location and might be varying with some probability at the same time as the gravitational wave event. So then we asked the question, so how many events do we need to confidently say that lambda is larger than 0? So some fraction of the binary black holes are actually coming from, are actually inducing AGN flares. So the number of events that we need to follow up is obviously dependent on the true value of lambda. So if there's more binary black hole events happening in AGNs, then you'll need to follow up less of those events to make this confident association, and vice versa. If you have just something like 10% of these events happening in AGNs, then you'll need to follow up more of those events to build up your confident association. And so these lines are just showing you how many of those events you need as functional lambda for different localization volumes. So like GW19 521 is up here. So you'll need, depending on the value of lambda, something like between a dozen and close to 1,000 events to build this confident association. While if we're just looking at the best localized events that we expect from the next observing run, so here I'm calling them the top 5%, is actually, the top 5% is actually a combination of volume and also of mass of the total mass of the binary, because we are modeling this expecting that you might have a brighter flare if the mass of the binary is larger, as it's the expectation from the model that was used to fit that flare that we've seen in the previous slide. So basically, this is a combination. This is a combination of these two things that is telling you how many background events do you expect to have, right? So if you pick just the events that are expected to have a smaller number of background AGN flares, then you need as many events as shown in this orange curve. So, so if what we find is that as long as lambda is larger than 10%, we need something that is about 10 events of this best events to make a confident association, and this should be possible within the next observing run, obviously with huge uncertainties on the rates. So we'll see what happens. Now, the last thing I want to mention about this channel in particular is that the one thing that we can propose with these AGN flares is also to use them as standard sirens, even though we don't know whether all of those flares that we might observe are actually associated with the gravitational wave event. But we can use the similar formalism that I showed you before to not only constrain the parameter lambda, but also constraining cosmological parameters by taking into account the fact that some of those events will not be associated with the gravitational waves. And so this is what I'm showing you here as an example, trying to constrain both lambda and the Hubble constant from an example of 10 of these well-localized events from LIGO, Virgo, and Cagra at the sign sensitivity. And here you see the constraint is actually competitive with the bright standard siren measurement from 170817, for example. And so I'm currently planning actually to follow up these events with a dark energy camera, hopefully in the next year. And the last thing is that obviously, most of these binary black holes are not very nearby as the binary neutron stars that we discussed before, but they go out to larger redshifts. So obviously one might prefer to expand the parameter space to explore beyond the Hubble constant. So we're currently running simulations to try and see how well we can constrain other cosmological parameters. So for example, here showing you a WCDM kind of scenario constraining also omega matter and W beyond H0. So to conclude, there is a lot of synergies between gravitational wave experiments and optical sky surveys. So in particular, in terms of the counterpart discovery, right, we've seen how DCAM was able to find the first optical counterpart. Hopefully DESI might be able to provide some, also help with a quick classification for a quick identification of the counterparts. And we can use those as standard sirens to measure H0. In the future also, hopefully dark energy, the dark energy equation of state already with the AGN flares. In the more distant future, we'll be able to measure also F sigma 8 and gamma with peculiar velocities. And also with a cross correlation with galaxy catalogs, we can also study an AGN catalog. We can also study the origin of binary black holes. Even for events without counterparts, right? That's true. And we can also use them to constrain the Hubble constant. And we expect that we'll be able to reach the 2% statistical precision on H0, also from the dark standard siren method, as soon as we start getting to the hundreds of well-localized detections. And I'll stop here and take questions. Thank you for listening.
Thanks a lot for this great informative talk. If you have questions, use the raise hand button or just unmute. While people are still finding the button, I'll start with a quick question. So you said that you need 50 bright sources or 200 dark sources to solve the Hubble tension, or to distinguish between the two values. Could you just quickly say what numbers we have currently, of how many sources have we observed so far?
Sure. So in terms of the dark standard sirens, yeah, we're talking about hundreds. And at the moment we are at, the well localized that I'm taking into account, they are in the order of 10. So right, just about 90, depends how you make your where you make the cut in SNR, for example, like how many detections you have, but that's the order of magnitude where we are right now. But we do expect that to increase significantly in the next observing round, because in the meantime, right, when the detectors are down, they're being upgraded. And so the number of detections kind of goes exponentially. And so, yeah, we do expect to be able to get to that 200 with a few years of run at design sensitivity. So actually we will not have a few years at design sensitivity, so we'll have LIGO and Virgo. And I should say that I'm not in LIGO or Virgo, so since you're recording this, so by no means take this as a statement from the collaborations, but what I know from their announcements is that the LIGO and Virgo will be running close to design sensitivity for the next observing run, and that will be about a year long. Gara will not be, so that kind of changes the kind of the forecast that I'm giving you here. But then in 05, the following observing run that could be a couple of years long, probably around 2026, then we'll have the A+ upgrade for the LIGO detectors, maybe LIGO India joining at some point, and also hopefully Kagra design sensitivity. So I think after 2 years of 05, we'll definitely have these detections, this few hundreds of well-localized detections.
Okay, thanks. See, Amal has raised his hand.
Hello, thanks, Antonella, for a nice talk. So I have 2 questions. One of them is that I think you showed that with DESI, you did some follow-up observations, right? So I want to know, what is the current policy? I mean, if there are some alerts, how fast and in what condition, for example, DESI can be used for the follow-up?
Yeah, so there is no policy right now, because I think, so that was part of a secondary target program. And I think that the secondary target programs call will come out again, hopefully soon, because the idea was to start doing it for year 2 observation. So hopefully we start year 2, I think end of September or beginning of October. So it could be in the similar timescale, and LIGO is supposed to start engineering run in November. So we'll know soon. But I think that the general feeling is that we might be able to do of those dedicated tiles, maybe like a few per year. If we make a case that, this is probably the only year that DESI will be overlapping with LIGO Virgo detections, maybe we can have a few more. But that's definitely enough, because we expect something like 10 binary neutral star detections in the entire year. And obviously you cannot observe all of them, right, with DESI. So if we can do 5, I think that's really all that we need. And obviously also they will not all be well localized, but yeah, if we can do something like 5, I think it's reasonable, and it's not crazy.
But do you think the follow-ups can be done quickly? I mean, how fast we can?
Yeah, I mean, for example, for the the target of opportunities that we're doing right now are just fiber assignments, and we just update this TO ledger, and because the fiber assignment is running on the fly during the night, you don't need any really human intervention, but you need some human intervention to say, this is the pointing that we'll want to take tonight. So, but I think anyway, the best strategy in my idea is to wait for the imaging programs to send out the imaging candidates. So it will still be 2 days. So we do have time. I don't think we need to stress out to go.
So it would be of the order of few days, which is
2 days, I would say. Yeah, that would be the best.
Okay, and I have one, if Benedict, if there is time, I can ask one question also about this 2% with 200. Did you consider the cosmology uncertainty there? I mean, there is usually when we deal with the dark sirens, we have to assume the background cosmology, right? And I think I have a paper with Ryan and Eric Linder a couple of years ago, which showed that when the precision goes higher, the background cosmology would actually be very important.
Yeah, no, I did not take that into account in that measurement. What I will say is that because we're really just using the best localized events that are also the most nearby events.
Nearbys are fine.
Yeah, we don't expect it to be a huge contribution, but you're right that we should be taking that into account. Yes.
Okay, thank you.
Thank you.
Okay, yeah. So thank you very much for your nice talk. Actually, about the dark standard sirens, especially for the galaxy survey data. So I wonder whether there is any sweet spot or optimal redshift range for the redshift survey data. The reason I'm asking is, for example, there will be SPX data will produce a huge photometric redshift data set. So I wonder which one is more helpful in terms of the cross correlation or large scale structure study.
So sorry, I didn't fully understand the question. I think I missed a couple of words.
Yeah, sorry. So the main point is for example the photometric redshift survey versus the spectroscopic survey, and which one would be better in terms of because there are pros and cons, right?
Yeah, that's a very good point. I think the answer will be in those tests that we really need to start understanding, like what are the host galaxies of these binary black holes, right? I think that will be really the answer. So I don't have an answer right now, but yeah, we should start analyzing, what type of host galaxies do we expect if most of these binary black holes are coming from globular clusters versus AGNs that maybe are selecting the most massive galaxies because these are the most massive AGNs. And so then, something like the BGS sample in DESI would be fantastic, and we don't need to be super complete like in the imaging catalog. And so that would be better. So yeah, I don't have an answer right now, but I would say that several formation channels, I think we would predict that we should be looking at the most massive galaxies, and so probably DESI spectroscopy will win.
I don't know if I can add one more. So the redshift range that you analyze in your paper, it seems all the sources are in terms of redshift is below 0.1. So I wonder, having the DESI sample, I mean, probably you can have used the bright galaxy sample. So having the redshift survey data, for example, the below redshift 0.1, is it good enough for the analysis, or you still need the high redshift survey data?
No, you still need higher redshifts. Obviously, it depends on like what your prior on H0, right? Like where, given the distance of these events, right, and your prior on H0, that's how far you're trying to go in terms of redshift. But I think that for the type of selection that I'm making, I think the BGS sample would be fantastic. It would just be the perfect, yes. So yeah, it would go beyond 0.1 given the the distances that we're taking into account and the H0 prior that is very broad that we're using. But BGS would be perfect.
Okay, thank you.
Thank you.
We're already a bit past the time, so I suggest to close here. Thanks, Antonella, for taking the time in your